So we'll be waiting for a few more minutes before people will enter the room.
So maybe I can say one sentence of explanation. This session that is happening now in Zoom is also streamed on YouTube, and about 2/3 of the registered participants have the ability to watch this in YouTube, and the other third has the ability to participate in Zoom.
Oh, that's great.
Okay, so I think it's time to begin. So welcome everybody to the first session of ICALP and LICS conferences, taking place virtually for the very first time. And I hope that this new format of the conference will allow us broader access to the highlights in our area and to the great research that people have been doing in the last years. So it's my pleasure to introduce our first speaker at the conference, join ICALP LICS plenary speaker, Professor Andrew Yao from Tsinghua University in Beijing. Andy Yao received his graduate degree in physics from the National University of Taiwan. Then he moved to Forward, where he received a PhD, and again, this was in physics. A good thing for all of us, shortly after he decided to study and enter the PhD program in computer science in University of Illinois at Urbana-Champaign. Then after graduating in 1975, he started his marvelous academic career in computer science. And first from 1975 until 2004, he has been working in the United States as a faculty at MIT, Stanford, UC Berkeley, and Princeton. Then in 2004, he moved to China to become a professor in the Center for Advanced Study and director of the Institute for Theoretical Computer Science at Tsinghua University. Since 2011, he is also a dean at the Institute for Interdisciplinary Information Sciences at Tsinghua University. While in China, he has built the foundations and created a great program in theoretical computer science. And by inspiring the next generation of researchers, he made China a powerhouse in theoretical computer science. He is a member of the US National Academy of Sciences and Chinese National Academy of Science. And actually, I think this He is a member twice, first as a foreign member and then also as a regular member. He is also a member of the American Academy of Art and Sciences. He has won many prizes in the course of his distinguished career, and this includes George Polya Prize in 1987, Donald Knuth Prize in 1996, and in year 2000 he was awarded the highest prize in computing, the Turing Award. This has been in recognition of his fundamental contributions to the theory of computation, including the complexity-based theory of pseudorandom number generator, cryptography, and communication complexity. He has been working in many different areas, and he has made fundamental contributions to many of them, including theory of algorithms, theory of data structures. He is considered as one of the founders of modern complexity theory, communication complexity, randomized algorithms, theory of pseudo-randomness, complexity-based cryptography, public key cryptography, theoretical foundations of quantum computing, and many, many other areas, and including algorithmic game theory, and recently he has been studying Bitcoin. He is widely recognized both as a great problem solver, resolving numerous important problems in theoretical computer science, and also a great visionary, developing new fundamental techniques and establishing new research areas, advancing computer science. Please join me in welcoming our ICALP LICS plenary speaker, Andy Yao.
Well, thank you very much to the chair for the generous introduction. And it's a great pleasure to be invited and have a chance to interact with all of you. And I would like to particularly thank Arthur and the organizing committee for giving me this opportunity. And I would have been very worried about giving an online lecture, except that in the past 6 months, all Tsinghua University has been on this online mode. So I've got a lot of practice during this. So ladies and gentlemen, again, it's a great pleasure. And in the last few years, I've been interested in mechanism design, especially the auction theory for maximizing revenue. And the topic I would like to talk about today is about the application of auction theory in Bitcoin designs. So before going to the scientific problem, I would like to briefly review blockchain and Bitcoin, just to put the technical result into the right framework and the language. And so I would like to start with talking a little bit about blockchain and the issue of security incentive, and then we'll go into the technical formulation of the question. So what's a blockchain? I think that most of us have encountered blockchain one way or another. And so let me just go over it very briefly. So from the application perspective, a blockchain, it's simply a distributed ledger and a database. And the main features of this entity is immutable and is decentralized. That means that it's very hard for anybody trying to erase the record or doing manipulation of the records. And the interesting part of blockchain, and actually I would think that it is one of the showcase for our collective effort in computer science, because it really is using most of the achievements that we have built in the last 40 years and it's built on mathematics, cryptography, internet programming, and many other fields of computer technology. And historically, it's invented by a person, or it could be a group of people that we're not sure, using the pseudonym Satoshi Nakamoto in 2008. And it involves key ideas from information science. And basically, these are concepts that we are all familiar with in computer science. The first key idea is the one-way hash function, and the second is to use distributed consensus. And so one-way hash function, it's simply a way of hash a data of any size into a string of a different size. And typically it could be much smaller, and it can be considered as a digital fingerprint of the data. And this hash function has the property that is very easy to compute the hash of any data. But on the other hand, if I have the fingerprints, if I have the hash value, it's hard to figure out what the original data would be. And a one-way hash function would have two major characteristics. Firstly, it's hard to figure out the raw data from the hash value. And furthermore, it actually, it's hard to find two different data with identical fingerprints. So, and the application of one-way hash function is very wide. It could be used to check data integrity, generating digital signatures, or verifying identity. And now, how do we use one-way hash function in order to create a database that is immutable? So let's just imagine that you have a transaction, you have a payment received on a certain order to the database, and what you would like to do is to create a linked structure of all the data as a log and with the date specified on it, and hopefully you would like this to be a permanent record. But the problem is that somebody might delete a record from it, and so hash function can be used to perform a fingerprinting copy of the data. So basically, what you can have, what you would like to have, is to at each record, instead of just appending the record, you would take a fingerprints of what happens in the last record. And so if you organize a chain like this, then you would have the property that is very hard to delete a record without finding out. So if I want to delete a record, I essentially have to delete everything after it. And so it would be much easier to be detectable. And now, but now, this is a great way of starting on designing a mutable database and record. But how about somebody who would try to eliminate the whole thing? And well, this involves the second key idea, is to do a distributed consensus. What it means is that what we can do is to use our knowledge about distributed computing, how to distribute data over the whole internet. So whatever you have built, if you send it widely distributed to everybody, then it would not be possible for any single entity trying to destroy the record. And the difficulty is that in a distributed system is a central and difficult problem to achieve distributed consensus, which enables all the users to have the same log. And now the distributed consensus, the goal is to keep the same log, and so it makes the same log, which becomes the common knowledge of everyone. And now, how do you add new entrant, new record into the the chain that is already there. Well, there are two types of methods. One is by proof of work, and also a later version is to use the proof of stake. And for our purpose, since Bitcoin is in the form of using proof of work, so let's go over it a little bit so that it will put our technical problem into the right context. For the proof of work, when you want to add new blocks, there are many candidate blocks, and each generated by a participant called a miner that would compete in solving a puzzle. And the winners may join the chain. And this process is called mining. And then there are the other ways of doing it through election. But let's focus on the proof of work. And basically, the miner would compete in order to acquire the privilege of adding a block to the chain that is already there. And in this block, the miner can solicit people to put their transaction in it. And so this division of labor is a characteristic of the Bitcoin. And now, so the miner would do the work using computing time and the equipment. And so they have to be incentivized in order to do that. And now the users who would like to put their record into this block would have to give something to the miner. So this is the ecology of the Bitcoin. So we'll say a little bit more in a while. Okay. So now there are pros and cons of the proof of work and the proof of stake. But since that's not the main focus of this talk, so we'll just take the proof of work as our operational mode. And now in blockchains, in particular the Bitcoins, there are important issues that are still very much actively worked upon. And basically it creates a lot of interesting difficult problems. One is security, and another major one is the incentive. Now, the major security goal is to ensure, technically, to ensure the persistence and the liveness of the chain, of the structure. And all users have the same view of the main chain, except perhaps for the last few blocks. And the liveliness is to make sure that adversaries cannot succeed in keeping honest users' block from being added to the chain. And now that's a very technically difficult question, because when you are involved with distributed computing and you have a stochastic process of competing for the privilege of adding the blocks, and if there are adversaries who is trying to disrupt the process, so it's a very big cryptography questions, plus the issue of stochastic analysis of the very complex process. And for blockchains, it's basically still very much unresolved, and we haven't found a really perfect solution that would be theoretically secure and practically can support the volume of the practical applications. Now, the second issue is about incentives. In order for people to participate, and actually, one of the big things for blockchain is really you want people to use it, because then otherwise it doesn't serve any purpose, and the distributed consensus will not work. So to provide incentive for miners who would spend a lot of energy in equipment and time, you have to give them incentives. Now in Bitcoin, the method is as follows. A miner's incentive for participating in the competition to solve puzzles is from two sources. One is to getting rewards from the system, and whenever you succeed in solving a puzzle, and you will get a certain amount of bitcoins for you, and the value of the bitcoins is according to the market price, and which is quite substantial by now. And the other way of getting reward is to collect transaction fees from the users. So there will be users who would like to put their record into the block that you have succeeded in adding to the chain, and you can charge the users for the privilege of putting their record in your block. And now, right now, both rewards are pretty important for miners, but at some point, supposedly that the reward from the Bitcoin system would cease, and it will be entirely supported by collecting transaction fees. And so there are issues like this. The question is that what would be the best way to incentivize miners, and what would be a fair way, and also what are the consequences of having a drastic change when the time comes that the only reward that the miners get are collecting transaction fees. And this have generated very interesting and lively research. And today, our question is really focused on this limited issue of the how the miners should collect the transaction fees from the users. So it's a very narrowly defined issue, and you can see that it generates some really deep and interesting questions in basically a stochastic model that is quite non-trivial to solve. So what I would like to do next is to formulate these questions in a more precise way and tell you the results that we have obtained on this. And so these are the Bitcoin, the supply of Bitcoins, and basically at some point that they will no longer produce Bitcoins, and the system will be really function more as a distributed system that people can generate immutable logs. And now we have finished with the basic framework. So let's look at the technical question of designing fee structures for Bitcoins. So as I mentioned before, that in the Bitcoin systems, there are essentially two kinds of participants. There are users who would like to put their transactions into the public record, and there are miners who would create blocks so that these blocks will be added to the chain. And now the miners will select the bits from the users who would like to put their transactions into the block. And for it actually is a complicated system since there are many miners and many users, but for the purpose of the discussion, let's just think about the very simplified situation in which there's one miner, and this miner has generated a block. And the question is that how does the block select users to include their transactions into the block? And so we can think of the users as putting their bits on the public record. So the user one would bid B1, and the user two would bid B2, and so on. And where BI is the amount, the number of Bitcoins or the number of dollars that she's willing to pay for putting the transaction into the block. And right now, the design of the Bitcoin fee is a pay your bid type of mechanism. So the miner would simply put the bids into a decreasingly sorted order. So for example, suppose the sorted list is $18, $13, and so on. And so the miner would take as many as possible until the block has run out of space. And basically, the miner would just charge the amount that the maximum amount that the bidders have pledged to pay for it. And however, in terms of mechanism design, this has some undesirable properties, even though this is a very simple, easily implemented mechanism. However, it has the consequence that the miner usually probably will collect really low revenue, because if you charge people in this manner, then there's a tendency for people who could have afforded a much higher amount into claiming a much lower value, because that as long as you get your block accepted, why not pay a lower price? So in the eyes of mechanism design, we wouldn't want this to happen. And ideally, in mechanism design, the gold standard is that you would like to design a mechanism of collecting fees in such a way that the bidders, if they change their bid, they will receive no benefit. So in other words, in mechanism design, people are very interested in designing mechanisms which are incentive compatible, and figure out that within the framework of incentive compatible, what would be the best way to design a good mechanism so that you can collect the maximum amount of revenue from the bidders. And unfortunately, this very simple pay your bid current way of charging is a very lousy mechanism in terms of that that is not truthful. It's not incentive compatible. And now there is a natural alternative mechanism called monopolistic mechanism. This works as follows. Again, you put the bids into decreasingly sorted order, and however, instead of just taking as many as you can until you run out of space, the miner would try to see that if you charge a flat price, what's the maximum amount that you can collect, so that you collect the same amount of money from each successful bidders, then what's the best you can do? So mathematically, the miner would just take any value k within the capacity and look at if you take in the k highest bids, so the k winners, and charge them the same amount, bk. What is the optimal k that you would like to choose, so that you can maximize the revenue under this called a monopolistic price? And so, for example, let's look at the monopolistic mechanism for this particular example. If k is equal to 3, so what this means is that you would charge $10 for the first the 3 highest bidders, so you will get $30 as your revenue. On the other hand, if you want to take in 4 bidders and charge it at the value $7, you will get $28. And so it turns out that k equal to 3 and getting $30 is the maximum amount of value that you can get in this particular example. And so the question is that are the users, is this a good mechanism from the point of view of incentive compatible design? And now, however, it's easy to really see if you examine it that this mechanism design is not truly incentive compatible. The bidders may still bid low. Just look at this example that if you are the bidder who, the second bidder that you can afford $13, and suppose you claim that the value, the bidding you put is equal to 6 instead of 13, then you can see that instead of the miners taking 3 winners and charge $10, then in this new list, the miner would actually take in 4 winners and each charge at $6. So therefore, you will get a $24. Now, if you look at, so this certainly is bad for the miner, and it's very good for bidder 2, because originally the bidder would have paid $10. Then now it only pay $6. So this is 40% discount. So let me just clarify that if you use the monopolistic mechanism, then if you bid truthfully, then you don't pay $13, but you pay $10, because that's the miner would use this MP mechanism, would charge $10. And but now if you change it instead to 6, then you get a 40% discount. And so if you let the delta to be this ratio, this discount ratio, to be the maximum discount ratio among all bidders, the miner, if you use this notation to be the maximum for each of the bidders, then the miners would like that the delta, this fraction, to be really close to 0, because if this value, the saving, the discount saving is really small, is very close to 0, then there is little incentive for the bidders to lie. And then, even though it's not a strictly incentive mechanism, but it will, in practice, it will do a good job. And this mechanism was specifically proposed in their paper in 3 years ago, Lavi, Sata, and Zohar, and they asked the question that if you are willing to deviate from the present Bitcoin fee design, what would be a better scheme to design Bitcoin fee? And of course, this really is a complicated question. You have to look at the whole system from many angles, like stability and other things. But what they did as I think as a start, to look at the Bitcoin fee design problems and give a whole freedom to design it, this would be the simplest circumstance that one can ask meaningful questions. And so they studied it, and they did also a lot of experiment. And basically what they have found is that if you have a very large N, the total number of bidders is very large, then it's found out that the good news that actually this measure is very close to 0 as n goes to very large. And so more precisely, the mathematical setup is the following. You have a distribution function f drawn over a finite interval between 0 and d. And if you generate IID, so you have n bits, each one of them is distributed according to the distribution f, and you sort them, and now what's the outcome? If this is the sorted list of the bits for the minor. And so they found that experimentally this is true, but they couldn't prove it, and they conjecture that this actually is true. And so the first theorem in this ICALP paper is to show that analytically this is true. So this looks like a pretty innocent looking formula to prove, but there's a reason why it is difficult to do, because it turns out to be a type of problem that people have studied in distributed systems, and more generally in the analysis of probabilistic algorithms. So it involves some really delicate issues, and so it takes quite a bit of effort to prove this theorem. And and maybe later on, if someone is interested, I could give some intuition on why where the difficulty is for this. But I will not go into a technical discussion in detail on the proof of the theorem, and the outline is given in the printed version of the proceedings. And so this confirms their projectures, and they have done a lot of experimental setup, and also involving cases when the distribution is over a infinite range, and so on. But I will not discuss those findings here. So just this is it's just one of the theorems proved in this paper, and there are other results that are related of this type that I will just leave it in the paper. But the consequence of the theorem is saying that this confirms the conjecture that this is a plausible design, and that the users will not be tempted to give false bits. And now, within this picture, as I mentioned, that there are different ways to formulate the Bitcoin fee design problem mathematically, and basically there's a lot of different type of attacks that one can think of. So therefore, if you examine this closely, you really should formulate the questions in many different frameworks, and each different attack would give you a different measure for which that you would like to analyze. And for example, there are attacks that involve splitting transactions. So there's one transaction I would like to put it in. How about splitting it into two transactions? And also the miner, from the miner side, the miner may have some trick that he can use in order to add or delete bits in order to get more revenue. And if you look at several different the versions, then it turns out that one can show that the theorem 1 actually still remains true. And now we turn into a different direction, and actually it's also looked at in the Lavi et al. Paper. And the question is that it's very nice that the MP seems to be something reasonable, and it's very close to incentive compatible in a statistical sense. But what about designing a strictly truthful mechanism and can you get something that have good revenue and but it's really incentive compatible. And so they have considered a mechanism which we'll call MP2, and this actually it's a version of an old version. It's a variant of something that is considered by Goldberg et al. A decade earlier. It's called the random sample optimal price mechanism, and the context was in the question of selling of auction for digital goods. So in other words, instead of the classical economics framework where you have a unique item and you would like to auction it to a bunch of buyers, in the Goldberg paper, they consider the digital version auctions where you have many copies of a goods and you would like to get a good price because essentially the digital goods can be sold at essentially zero cost. And now in our current context, this mechanism, which we call MP2, would be the following. Suppose you have the bid, the list of the bids as before. So the first step is just to randomly separate this bid into two parts. So, for example, in this case, we may have randomly selected the first item, the third bid, and the bid here, and also the other list is the remaining one. And basically, what you do is the following: for each bid, for each list, you would use the MP way in order to set a monopolistic price. So just regarding the list one, the B prime, as a list by itself, and you would like to use the criteria for the miner to find out what the monopolistic price is. So in this case, this would be 10, because for this list, if you use 10 as the threshold, then you can collect $20. But if you use 3, then you get only $9, and this you get $18. So this is the monopolistic price for the list B prime. And similarly, for the list B double prime, that 7 would be the optimal value for this thing here. And now we'll just let these two separate prices to be used on the other list. So this B prime is generated and computed on the list B prime, and now this is without participation of the bids from the other list. So therefore, if we include the bids from the list B double prime, then it's incentive compatible because it's independent of what you would do for the bidders on this list. And so similarly, so we'll just use this two monopolistic price to be used on the other list. And so as you can see, that the miner would take, in this case, we will take 13 from the list B double prime at a fee $10. And also the miner would take from the list B prime that the first two bits would be bigger than 7. So therefore, this would be the result of which bits are taken by the miners and at what price. And the revenue of this alternative mechanism then is $24. And so notice that this $24 is less than the $30 that we have before using MP. So it's a step down, but on the other hand, MP2 is truthful. So, and also experimentally, Lavi et al., they have done a lot of simulation, and they have found that MP2 gets less revenue than MP. And they have made a conjecture. And because they have found no counterexamples, they conjecture that this actually is always the case. So a second theorem in the current ICALP paper is that to confirm this conjecture is to show that if you use this incentive compatible mechanism, it's always you get less revenue than the monopolistic price. And so if you compare MP with the variant MP2, one is truthful and one is not truthful, but nearly truthful. And one gets less revenue, and while the MP gets more revenue, and the MP is simple to implement, and MP2 it's also easy to implement. So now we have two mechanisms that both are plausible candidates as the possible Bitcoin fee design. And so when we apply auction theory and using their criteria of incentive compatibility to Bitcoin and in general blockchain design, it offers very interesting challenges for the theorists and the system designers alike. So I think that the paper by Lavi et al. In our analysis really is just the beginning of for the theorists on how to do such things. And let me just conclude by saying that the blockchain provides a rich source of new research problems. The security and incentive design generates novel, intriguing, non-trivial, but tractable and sometimes intractable questions for stochastic analysis, game theory, mechanism design, etc. And the blockchain, so this is really is a advertisement for a subject that I'm quite enthusiastic about, that as an academic subject, it reignites passions for some traditional subject. For example, the theorems that I approve, these are really classical algorithm analysis subjects. And I think that at some point in the past, people no longer regard it as something that is very exciting, even though it's intellectually interesting. But I think that it turns out that having a great knowledge pool is really great, because those kind of knowledge and technique enable us to be able to get into the research frontier for things like blockchain in a really easy manner. And of course, I think that even more than that, I think that the security question is really it's a gold mine for applying all the knowledge we have accumulated in cryptography, such as zero knowledge proofs, the multi-party secure computations, and these are things that would enable much more blockchain applications. And in fact, it's something that there's a lot of interesting research going on in this sphere. For example, the Zcash, and also the blockchain is intrinsically interdisciplinary and is still in the early stage of development. And so I will finish my talk. Thank you very much for listening.
Thank you very much. So let me just be the only person here to clap. So thank you very much for this exciting talk. Now we'll have time for some questions, and let me kind of explain the procedure. So we allow the participant to ask question on Slack, and I see already 2 questions that I will just read in a second. But if any of you later will be really interested in asking any questions, please just, hopefully in synchronized way, try to unmute and ask the question. So first, there are 2 questions from Slack, and actually, so first is by Anush. Maybe Anush, you could ask the question yourself, or you want me to read it?
Sure, I'm happy to ask it if you can hear me.
Yes.
Okay, my question was rather a general one. Early in the talk, you talked about the high energy costs of something like Bitcoin and proof of work. So I was wondering whether one should, in fact, look at incentive mechanisms for which incentivize reducing energy cost, and how one would formulate that.
Yes, I think that's a great question, and I think that usually people will try to solve the energy question by saying that let's switch to a different paradigm, so that we'll use the election type of paradigm to do the selection on a proof of stake basis. But the question that you phrased, I think, is an excellent one. So, are there rooms for thinking that you can still use proof of work, but you would save energy? I think that naively it will be very difficult to do, because I think that if you stick to the idea that when you generate a block, you would get rewarded by Bitcoins, and if you comes very cheaply, I think you could create the stability of the system, because suddenly you may be able, the market will be swashed with Bitcoins, and the Bitcoin value would drop. And of course, it's nobody says that the value of the Bitcoin should always go up automatically, but it does create a governing problem for the committee which runs the Bitcoin system. So I think it's a great question. I think that questions of this kind would generate, it could generate really exciting new ideas for further research.
Yeah, so there is a second question by Revanta. I don't really see her on Zoom, so maybe I'll just read it. So with large N, if there are a few initial false bits, could this change the scenario, violate the hypothesis of theorem 1 in a way that incentivizes further false bits? This is about stability of theorem 1.
So if you let n goes to infinity?
So with large N, if there are a few initial false bits, could this change the scenario, violate the hypothesis of theorem 1 in a way that incentivizes further false bits?
Yeah, I think that the theorem is only valid for a certain IID process, and so certainly in the real Bitcoin scenario, you could have things that really violate the hypothesis in a drastic way. If you have some really, if the bidders collude and violating the independence, and so anything that deviates from the mathematical hypothesis of the theorem, this could create problems. And so, I mean, that's why I mentioned that this really is just a taste of what kind of intellectual theoretical questions that you might be able to frame and solve. And but certainly, the exciting part of Bitcoin and blockchain is that it really is not a rigidly formulated questions, and in order to have real applications, one has to understand the environment where the blockchain is used. And so this would this means that to have research that can produce good solutions really have to be a interdisciplinary effort. Well, certainly it should go across different areas in computer science, and people who are theoreticians, and people who are system designers, and people who are psychologists, in order to figure out what would be the correct, would be a good really a framework, so that the solution that you produce will not run into disasters.
Excellent, thank you. So there is a next question by Andre Nusser. Do you believe that a different paradigm can be similarly robust as proof of work?
I think so, because I think that usually I know that there are impossibility theorems, and I'm one of the fans of impossibility theorems, but many years of experience show me that usually the naysayers, the impossible type of frame of mind, usually would be on the wrong side. So my own belief is that one really should think positively about trying to build better and better mechanisms. So I believe that there are some really yet undiscovered and actually could be quite simple designs for blockchains that would be ideal from many respects. It's true that the proof of stake, the type of proposed systems right now, that there are weaknesses, and the stability question, it's something that is difficult to guarantee. So I think the answer is that I think the answer is yes, and that's good news.
Okay. There is one more question, and let me just try to copy it. Okay, so let me read it. It's longer. So it's by Eric Yan. Is Eric Yan online? Could you maybe unmute and ask the question? Oh, okay. Okay, so let me read it. The conjecture by Lavi et al. That you proved in your ICALP paper shows that MP2 is smaller than MP. Could it be the case that MP2 is within a constant factor of MP? Or they can be arbitrarily far apart? So somehow the question is, how close is MP1 and MP and MP2?
I think it's a great question. I have not looked at it, and it seems naively that it shouldn't differ too much from the from MP in the stochastic sense. That certainly I believe that if you divide the whole list into two sublists, I think that is probably true, that you can always find some really bad way of separating these two parts. However, if you do it randomly as defined by the MP2 mechanism, I think that it probably is true that you can prove that the MP2 is greater than say lambda times MP revenue, with the lambda fairly close to 1. So that would be my conjecture, but I think it's a great interesting question, and I think it would be non-trivial also.
Okay, Excellent. So now we have another question from Amitabh Trehan. Does your analysis require proof of work or is independent of any such mechanism?
This one is independent of the proof of work. As long as you have two kinds of participants. One, like miner, who would supply the vehicle for carrying transactions, and the other group of people are just usual users who are not interested in the system, who simply want their transaction to be carried by this medium. Then the fee collection framework would be identical. But let me say that the Bitcoin fee is really only it's only is one part of the revenue questions, the financial aspect of the of blockchains. I think that if you think about blockchain in its full glory and supporting many applications, I think that the question of the of how do you compensate people, the revenue generation, and how do you distribute and the financial dependencies between the various groups of participants. I think it would be a very extremely interesting type of question that I don't believe that we have seen it discussed too much. And I believe there is a really very deep of riches that are created by the blockchain that would provide great research questions.
Okay, let me ask the last question from Slack by Peter van M. de Bosch. Does the mechanism guarantee that eventually all bidders are served?
Yes, I think that's the kind of the security. That's the security portion of the work. If you design the Bitcoin properly, if you have parameters that your system can support, then ideally you should. So the persistent question and the liveness question would guarantee that everything you would like to be put into the public record will eventually it will be selected and added to the blockchain. And but those are really difficult analysis, and it's the mathematical rigor that we can provide for systems that are capable of operating. It doesn't match us up to the applications that is intended to. So I think that so this looks like a field that's in some way it's a little bit shaky in terms of the theoretical guarantees, and so we'll do the best we can, and we do simulations, and we'll let it to be run, and we hope that the system will not be swamped, but I think that eventually we should be able to design ideal systems that really have rigorously provable mathematics that matches the parameters for which the applications are designed for.
Thank you very much, Andy. I think that we have to finish now. So if there are any more questions, and I see, for example, that Amitabh, he kind of slightly revised the question, please put the question on the Slack. And I hope that Andy will be able to respond to these questions later. And I would like to thank Andrew Yao for his great talk. Thank you once again. And
thank you very much, Arthur. Let me clap too. Thanks very much, Arthur. and thanks the audience for
Yeah, thank you.
for stay with us. Thank you.
Thank you.
Bye-bye.
And now I think we'll move to the next session. Yeah.